Okay, so in this first question up here, we are looking for heat, and since we're looking for heat, what, can you tell me what unit we're looking for? Calories. So the answer has to have units of calories. So we've got calories up here, but we also have grams and degrees Celsius. So don't get confused when it says heat. Don't go to temperature. Don't go to degrees Celsius, because those are not the same thing. So we need this unit right here to be in the answer. So it needs to say calories somewhere out here. So the way I'm going to set this up is, I'm not going to bother using the formula. I'm just going to use the railroad track method to do this. So what we have here is 0.22 calories per gram degrees C. Why did I write that in the railroad track thing in that format?
Because you have calories in the grams.
Divided by.
No.
I want to end up in calories.
I want to end up with calories as my only unit, and that unit needs to be in the numerator. The number won't always be in the numerator, but in this case, we want it to be in the numerator. So I wrote the only measurement I have that has calories in it in a way that gives me calories in the end. The problem is that this unit came with the grams and degrees C, so I need to get rid of that. So I'm going to start with the 75 grams, and so I'm going to write 75 grams up here. How come?
Because you're trying to get rid of the grams.
Because I'm trying to get rid of the grams, so if I write that in the numerator like that, then the grams that's in the numerator will now cancel out with that grams in the denominator. Okay. So there's one little tricky part to this next thing, though, is I need now to get rid of the degrees C, but I have 2 degrees C numbers. And so what we need to do is understand what specific heat is. What is specific heat?
It's final temperature minus subtract the initial.
No, that's the delta T. What is specific heat?
Oh, the specific heat of what?
Oh, it raises it 1 degree Celsius.
What? I thought I heard.
How much heat it takes to go up a degree.
Okay, so what's an easy way to say that?
How much it takes to heat something up.
Yeah, is it easy or is it hard to heat something? That's what specific heat is. So what we're talking about is increasing or decreasing something's temperature. So the temperature that I have to put in here isn't going to be the final temperature or the initial temperature. It's got to be the what?
The specific temperature.
The difference.
The difference.
Oh, the difference.
The difference. I started it at 3 degrees Celsius. So do I put that number in there? No, because it's not 3 degrees Celsius after the heat's been added to it. And I'm not going to put 110 degrees Celsius in there because it wasn't I didn't increase its temperature by 110 degrees. I only increased it by how much? 107. So that's the only little tricky thing. We got to remember that it's only 107 degrees Celsius that I'm going to put up here because I already started at 3 and I went up to 110. So then whatever the difference is has to do with the amount of heat that was added. So then I can go and cross off my degrees Celsius now, and that degrees Celsius. And what's the only unit I have left? It's the only is this calorie unit, and that's what I'm looking for, this calorie. So then I can hit equals and 0.22 times 75 times 107. Does somebody have that?
1965.
Really? 1965, what?
0.5.
0.5?
And then that would make it 19.
Is that what everybody, we got some confirmation on 1965? 1765? All right, let's try that again. 1765. And so 1765 calories, but if I go back to my problem, it's about sig figs, right? So this guy has 2 sig figs. So this guy this guy has 3. This guy has 2. This guy has 2. And this guy has 2. So my answer can only be in 2 sig figs. So what's my answer going to be? 1800 would be the correct answer for that one. So that's how many calories was added to heat this thing from 3 to 110. Okay. Do we have questions about that one? All right, so I said this one was gonna be tricky, and you have to kind of remember something, a couple of things, to make this doable. So, when I look at a problem like this, I'm gonna start off by, what are we dropping in? Lead? So, I've got a chunk of lead, and I'm gonna drop this in a container. And so that's water. And so now I can kind of picture what's happening here. So I have a piece of lead, and the piece of lead is hotter than the water, because how do I know that? The water's temperatures rise. So what I'm trying to do is figure out, what is this guy's temperature? What is his temperature initial? Before it gets put into the water, what is its temperature? So I'm gonna have to do some back calculations here, really, is what ends up happening. What can I calculate right off the bat?
How much the water temperature rose?
Okay, so right away we can say that the water temperature rose 11 degrees Celsius, right? So let's start a little list here. So water. So my temperature, my change in temperature is 11 degrees Celsius for the water. What else do I know?
The mass.
Okay, so my mass of my water is 175 grams. What else do I know? Say again? Okay, so then I can start another little list here and say my lead is 75 grams. What else do I know?
I can't see all the questions.
What?
You can read the whole question that's up there, it shows what's all there.
Don't you have it with you?
When we turn
We turned it in.
You're supposed to print 2. That's what the homework says. Print 2, complete 1, turn it in, and then follow along with the other one. So do we know anything else?
No specific for both of them.
We can look the specific heat up for both of them, right? So the specific heat for the water is easy. It's
0.00.
1 calorie gram degree C. And the specific heat for the lead, what is it? Somebody have that?
0.038.
0.038? Perfect. Okay, now it comes the tricky part. We have we have one thing we need to understand, and we have one other piece of information we already know. What other piece of information do we know but isn't really obvious? So I know that the temperature of the water started at 11 and ended at 22. So I know that its change in temperature is 11, but what else do I know about that from my picture?
How much heat is needed to change the temperature?
I can calculate the temperature of the water, the change of, I can calculate the amount of heat that was added to the water to make its temperature go up 11, but I know one other piece of information.
The final temperature of the lead?
I know the final temperature of the lead, don't I? Why?
Because if it's in the bucket of water and the final temperature of the water is 22 degrees, then the lead is 22 degrees.
I put a piece of hot metal in some water, and the water temp went up. Why did the water temp stop going up? Because they equaled each other. At that point, at 22 degrees, now my lead and my water are at the same temp. So I know my final temperature of my lead, right? So that's going to be important. So, what else? So my temperature final is 11 degrees for my lead. Okay, but I can calculate how much heat that the water needed to increase its temp from 11 to 22. Oh, I'm sorry. Yeah, for the final temp. I think. 22. So I've got the amount of heat from the water. So it looks like my Q of my H2O, and so that's a heat, so I'm gonna put 1 calorie per gram degree C, and then my grams are 175, so the grams cancel, and then my change in temperature is 11 degrees Celsius, so that cancels out. And so I get 11 times 175 times 1. So 175 times 11. I get 1925 calories. So now this is how much heat the water gained. And from the a law of thermodynamics saying that energy is never created nor destroyed, the conservation of energy, what is that also telling me? The water gained 1925, therefore
The lead loss.
the lead lost 1925. So now I know the Q of the lead. So now I know the final temperature of the lead, and then I know the heat of the lead. So if the Q of the water is 1925, what's the Q of the lead? Negative 1925, right? It lost that much heat.
Oh, okay. Yeah.
Does that make sense? So that heat had to go somewhere, and it went from the lead to the water. So then that means my lead's heat loss was 1925. Okay, so if it lost 1925 calories, what are you going to say about its temperature? What must its temperature have done? Dropped, right? So what I'm looking for is the temperature. I want to know what the initial temperature is. I know what the final temperature is. So what I'm looking for is how much did this piece of lead's temperature change? Okay, so I need temperature. And so what I'm going to start off with is grams and degrees C divided by 0.38 calories. So this will be, this is for my lead. So why do I have the specific heat written upside down in this railroad track? I want to know how much the temperature changed. So I need temperature in the numerator. So I'm going to cancel out my grams by throwing in 75 grams down here. If I do that, then I can cancel my grams out. And then I'm going to put negative 1925 calories here. How come? So I can cancel out the calorie, and it's negative because that's how much the lead lost. So I'm going to divide that by 0.038. I'm going to divide that by 75. And so I get negative 675 degrees C. Am I done? I'm not done. Why not? Okay, I got a sig fig issue, but I got another problem though too. What is that negative 675 telling me? No, it's not cold. At no time would you ever consider this piece of lead cold.
Well, no, but it should be cold.
Nope.
You still have the 22 degrees Celsius.
Okay, so what's the 22 degrees Celsius? The final temperature. And what's this negative 675 C? No, it's not. It's not. It's the change in temperature.
Also, you have to add.
Does it make sense that the negative is a change in temperature? Because this thing can't be really cold, right? I agree that negative 675 is cold. It's actually way below absolute zero cold, so that's not a possibility. But this was never cold, right? Because it heated water up.
It's the drop.
It's the drop in the temperature. So if the temperature fell 675 degrees to 22 degrees, what was its starting temperature?
675 22 plus 675.
675 plus 22. And you can look at that, you can see that in the calculation. Its change in temperature is temperature final minus temperature initial, right? So if I'm looking for the initial temperature, which is right here, algebraically, if I solve for that, then its temperature initial is equal to temperature final minus change in temperature. Are we okay with me saying that? So now it's 22 minus minus 675. So then I get a big positive number. And 697. So then my temperature initial is 697 degrees Celsius. And I'm gonna say that it's 7.0 times 10 to the second degrees Celsius. Why did I write that? I only have two sig figs. I could have written 700 degrees Celsius, but what's bad about writing 700 degrees Celsius? You don't know if the other zero, it's 7, we know that's significant, and then the 0 right after that, is that significant or insignificant? I do know that the last one is insignificant, but I still don't know if the tens place is insignificant. But if I write it like this, I know that the 7 and the 0 are both significant, so there's no ambiguity about the answer, sig figs. Okay. Questions about that one? What makes both the Greek theory and Dalton's theory of the atom such a big, huge move forward in science? Why is this a big, big move forward?
Between the both of them, they accurately describe atoms and their composition.
Okay, so describing atoms, why is that important? Why is the fact that they decided to say that everything's made out of atoms an important thing? I mean, besides the fact that, they are.
Oh. Is it because nobody else wanted to believe that, maybe? Because they were criticized for it?
Well, that's one aspect of it, but what did they think that we were made of before this? Let's think about the Greek one. What were we all made of as far as the Greeks thought? What was everything made of? Cartoon called Avatar, movie called Airbender. 4 things.
Oh, earth, fire, wind, water.
Fire, earth, water, and air, right? Those are the 4 things that everybody's made of. Well, not really. Because fire isn't even actually a thing. It's just something that's undergoing a chemical reaction. So itself isn't. Air, sure, that's actually something. Earth is something. Fire, no, that isn't anything at all. So the problem was they didn't know what we were made of, and they didn't have anything to go on, so they just started making stuff up. So these two guys basically, I guess what would be a good way to say that? How about that? Pull back the curtain. What do people? What's everything made of? Anything. I can say whatever it is as long as the curtain's closed. I mean, the Wizard of Oz is a giant, huge, crazy wizard until you pull the curtain back and you realize he's a grizzled old man messing around with some machinery. So when nobody knew what it was, everybody could make up anything that they wanted. So when a guy walks into town and says he can make gold out of lead, and you see him make gold out of lead, what you think is, okay, I guess he knows more about how the world works than the rest of us do, when that's actually not really possible with what he was doing. So it gave everybody the ability to actually start doing research on stuff that was actually true. There was no more fantasy. Protons, protons and neutrons, where do you find these guys? Nucleus. And the electrons? Orbits, like that. What can you say about the magnitude of the charge on the proton relative to an electron? Magnitude of charge, proton, electron.
Protons are positive.
I'm only asking about the magnitude.
The charges are equally strong.
Period. End of it. They are equally strong. They are equal. That's perfect. I know that because most hydrogens are 1 proton and 1 electron. Are hydrogens charged? They're neutralized because there's one plus and one minus, so they cancel out. What does Dalton say happened during a chemical reaction?
Is that the one where it's atoms separate, combine, and other stuff? Yeah.
Combined, separated, and rearranged. That's what's happening. In your head, you should just picture a couple of Lego structures that get disassembled and put back together. There really isn't anything else going on. Nothing happens to the atoms themselves. They just get moved and hooked up in different ways. Why is Dalton happy to know that the chemical formula of water is H2O?
Have to do with the simple whole,
Simple whole number ratios. What is the ratio for this, for these atoms? 2 to 1. It really, I mean, 1 to 1 would be the most simple, right? This is the second most simple. It's 2 to 1 ratio. So that's what we're looking at, that the fact that all water molecules have this simple 2 to 1 ratio of hydrogens to oxygens. Any changes in that makes you not talk about water anymore. What did Thomson discover about the atom? Don't say plum pudding model, because that was wrong.
it had, on there, the outside of it was negatively, positively charged, and the inside of it made up of small.
How about that? If you can read that. A negative particle that can come off. That's what he figured out, right? The rest of what he said was incorrect. But he did get it's a negative particle and that thing can come off the atom. And in essence, this is the most important part of the entire process, right? Because does it really matter to us that the protons and neutrons are stuck in the nucleus? As far as chemistry goes, it totally doesn't. How often are you exposed to nuclear reactions? I mean, forgetting that the sun is a giant nuclear reaction. How often do you encounter nuclear reactions on a given day? Not. You don't encounter them. But you do encounter chemical reactions constantly. You are a giant bag of chemical reactions. And since chemical reactions are electrons and their actions, he basically found the most important part of it. This is the atom, this is the part of the atom that can come off, and this is the part of the atom that can do stuff. What does Rutherford discover about the atom?
It has a nuclei.
He finds out that the positive part is in center, tiny, and dense. That's what he figures out. The two of them together almost tell you the whole story about the atom. Not quite, but almost. And how about this? You are mostly empty space.
I said something like, the atom itself is a tiny nucleus with a bunch of empty space around it, and matter is made up of millions of atoms, which are mostly empty space, so everything that is matter, which is everything, is mostly empty space.
Okay. 99.9999% of matter is in nucleus. Okay? The other small percentage is the electron. That nucleus is how big compared to the atom? It's tiny. It is the distance across the atom. It's about a 1 to 10,000 ratio. So it's a dot in the middle of a 10,000 size atom.
Would you
So
say
if I'm saying that this is the atom, and I'm saying this is the atom because the electrons are rotating around this nucleus, the space between the electrons and the center, it's 10,000 times more empty space than the dot in the center of it. Yeah, it's probably more like a grain of sand in the middle of a baseball stadium, like the Astrodome or something like that. And so, yeah, there's a bunch of empty space in the Astrodome, and that one grain of sand is where all of the matter is. So, yeah, you're mostly empty space. And then there's one other aspect. What's the other piece? The atom itself is basically an empty shell of positive and negative, but what else is there?
space in between?
Yeah, then I also have space between atoms. That's all empty as well. What you mean by push